Today, we are peering deep, I mean really deep, into one of the Earth's most vital and, frankly, fragile mechanisms.
We are.
We're talking about the massive oceanic engine known as the Atlantic Meridional Overturning Circulation, or, as you've probably heard it called, the AMOC.
Yeah.
And if you've been following climate news at all, you know this system has moved from being like an obscure textbook topic to maybe the most immediate terrifying tipping point we face.
It is absolutely the highest of stakes. I mean,
Yeah.
the AMOC is essentially the regulator, the heat distributor for the entire northern hemisphere.
Just shapes everything.
It shapes our weather, our sea levels, the very distribution of life. And the core fear, which is, supported by a growing body of scientific evidence, is that this vital system is potentially headed toward an irreversible collapse.
And that's not just a scientific curiosity.
No, it's a true climate catastrophe.
And the reason this matters so acutely to, well, billions of people is its function. It's like a planetary radiator.
That's a great way to put it.
Imagine this massive silent pump pulling warm tropical surface water north. All that heat is what keeps Western Europe in particular so much warmer than its latitude would suggest. You take that heat away and the climate shifts dramatically and globally.
And the underlying cause of this instability is global warming, specifically the side effects, like the introduction of vast amounts of fresh water.
From the ice melt.
Exactly. And our listeners shared some fascinating sources that really dive deep into the resulting scientific tension, because we have a dramatic disagreement over timelines.
This is the crux of it, isn't it? The when.
It is. Some studies are issuing genuinely dire warnings, projecting a potential collapse starting as early as the middle of this century.
So within our lifetimes.
Potentially. But then on the other hand, you have other very recent, very prominent studies that dispute the whole methodology. They argue this circulation might be far more stable than we fear.
So we have this scientific conflict over when it might happen, but what about the what? Is there agreement on what a collapse would look like?
Oh, complete agreement. A shutdown would be a major, practically irreversible global event. The consensus is pretty solid on that.
How irreversible are we talking?
We're talking about a geological timescale. Recovery could take thousands of years. So for every human generation alive today, and for the foreseeable future, a collapse is permanent.
That is a chilling reality.
It is. If the AOC shuts down, the climate shifts are catastrophic, pervasive, and essentially permanent on any timescale that matters to human civilization.
Okay. So our mission today is to unpack this high-stakes debate. We're going to dissect the fundamental physics driving the AMOC, what fuels this engine. Then we'll get into the conflicting estimates on the timing of a collapse.
And we'll give special attention to the work of the sibling scientist whose mid-century forecast really shook the world.
All right. And finally, we have to address the most radical idea on the table. The geoengineering proposal to, of all things, close the Bering Strait.
A desperate measure for sure.
Okay, let's unpack this. We have to start with the fundamental physics of this ocean engine. What makes it tick, and why is it so fragile?
Well, to understand the AMOC, you have to think globally. Yes, it's the main current system in the Atlantic, but it's really the critical high-speed part of the global thermohaline circulation.
The ocean's global conveyor belt.
That's the one. The thermo refers to temperature, and haline refers to salt. Because at the end of the day, those two properties determine the density of the water, and density is what drives the whole system.
And its core function is just essential for heat distribution. We often talk about the Gulf Stream, right? The AMOC is the deep plumbing that makes the Gulf Stream so powerful.
Exactly. It's like a huge heat reservoir, funneling all that energy from the tropics up past the equator.
The scale of it must be immense.
It's almost incomprehensible. This current system is like a persistent thermal battery for the northern hemisphere. Warm, salty water flows north on the surface. When winter hits, all that stored heat, we're talking hundreds of trillions of kilowatt hours, is released into the atmosphere.
And then the winds carry it east.
Right, the prevailing winds carry it eastward. And that heat transfer is exactly why, if you compare London or Oslo to places at the same latitude in Canada, Europe enjoys this massively milder climate.
How much milder are we talking?
It's a huge heat benefit. It contributes anywhere between 4 and 10 degrees Celsius of warming to those northern regions.
That's a massive margin of difference. So what drives the water to complete the loop? It's not just a surface flow, right? It's like a massive underwater density waterfall.
That is a perfect analogy. The key mechanism is the overturning circulation. And it isn't driven by wind. It's driven by what's called water mass transformation way up in the North Atlantic.
In the Labrador and Nordic Seas?
Primarily there, yes. The warm, salty surface waters arrive from the south, and they're exposed to that cold, dense Arctic air. The water cools down significantly, and critically, a little bit of evaporation happens, which makes the salt even more concentrated.
So cooling and more salt means higher density.
Precisely. The water becomes so cold and so dense that it literally collapses into the deep ocean. This sinking water mass is what we call North Atlantic deep water, or NADW.
That's the engine room.
That is the engine room. Once this incredibly dense water sinks, it begins its slow, deep journey south, hugging the seafloor. And that deep flow drives the entire lower part of the system, completing the loop and pulling more warm surface water up from the tropics to replace what just sank.
It sounds beautifully self-sustaining, a classic feedback loop, but
Yeah.
I guess that's also why it's so vulnerable. Which brings us to this chicken and egg mechanism.
This is where we get into the famous concept of the salt transport feedback. It was identified by an oceanographer named Henry Stommel way back in 1961.
What did he figure out?
Stommel realized the AMOC is fundamentally beastable. It basically has two modes: on, which is strong, and off, which is weak or collapsed. The system is strong because the North Atlantic is salty.
And it stays salty.
It stays salty because the AMOC brings a constant, immense stream of salty water up from the subtropics, which is a place where there's a net evaporation.
So the AMOC relies on the very salt it transports to keep flowing. If you interrupt that delivery, the whole thing grinds to a halt.
That's the tipping mechanism. It's called the Stommel bifurcation. If the northern Atlantic suddenly gets a massive input of fresh water, it becomes, well, fresher. The water is less dense.
And the sinking slows down.
The sinking mechanism is inhibited, yes. And as the AMOC slows, less salty water is drawn up from the tropics, making the North Atlantic even fresher over time.
Which creates a self-amplifying, vicious circle.
Exactly. And if the AMOC's strength drops below a critical threshold, the system can just abruptly transition to the off state, where it pretty much stops overturning.
Okay, so the natural question now is, what is supplying all this fresh water in the modern era? I mean, this isn't just a theoretical concept anymore. We have a real, measurable destabilizing factor.
Absolutely. The primary modern destabilizing factor is the unprecedented rate of ice melt, all driven by global warming.
The Greenland ice sheet.
Freshwater input, especially from the massive and rapidly melting Greenland ice sheet, is flowing directly into the subpolar North Atlantic. And this injection of freshwater, it acts like a lubricant. It reduces the water's density and effectively smothers the engine that drives the sinking.
The sheer volume must be staggering.
It is. The scale is what makes this so critical. Sources indicate that since 1993, the melting Greenland ice sheet has added about 5,000 cubic kilometers of fresh water to the subpolar North Atlantic.
5,000 cubic kilometers? That's hard to visualize.
Well, think of it this way. That volume is enough to cover the entire state of Texas with about a foot of water.
Wow. Okay.
And this continuous dilution, it weakens the stratification, preventing the deep, dense sinking needed to maintain the circulation. It's the primary reason why modelers and observers are so concerned about crossing that Stommel threshold sometime this century.
So the physics tells us the system is vulnerable, that it can be tipped by fresh water. But the crucial scientific challenge now is figuring out, is it already tipping? I mean, we can't wait for the engine to completely stop before we know it's broken. So scientists are looking for these subtle but measurable advance warnings. This idea of critical slowing down.
Critical slowing down is a phenomenon you see across all kinds of complex systems, ecosystems, financial markets, as they get close to a bifurcation point, a tipping point.
How does it work?
Well, when a system is stable, far from tipping, if you disturb it, say a short cold snap or a pulse of fresh water, it recovers quickly. It just snaps back to its stable state.
But as it gets closer to the edge,
As it gets closer to the threshold, that ability to recover weakens dramatically.
so the system gets sluggish, it takes longer and longer to forget the disturbance.
Precisely. It gains memory. The system starts taking forever to return to its baseline, which tells you its stability is getting shallower. And this change is measurable
How so?
through indicators like the autocorrelation function, or ACF. An upward trend in the ACF means the system's state today is highly correlated with its state several years ago. It reflects that sluggish recovery time.
So finding a rising ACF in the AMOC data would be a huge red flag.
It would be a powerful physics-based warning sign that we are close to the precipice. regardless of what the overall strength measurement is telling us at that moment.
That's the theory, but for the general public, the most cited, tangible piece of evidence that the AMOC is failing is this cold blob phenomenon. It's a really remarkable visual fingerprint on the map.
The cold blob, or the warming hole, is maybe the most convincing indirect proof we have. It's this persistent, large pocket of unusually cold surface water located directly south of Greenland in the Labrador Sea.
And it stands out because the rest of the planet is warming.
It stands out like a sore thumb against the inexorable backdrop of steady global warming pretty much everywhere else over the last century.
So why is this feature so inextricably linked to the AMOC?
Because a weaker AMOC is less efficient at its primary job, which is delivering tropical heat northwards. If the engine slows, that specific region, the destination for the warm water conveyor belt, gets less energy.
So it cools down.
It cools, or at least it fails to warm like the surrounding waters. And crucially, this isn't just a fleeting surface anomaly. The cold blob is visible in the integrated ocean heat content of the upper 2,000 meters.
So it's deep.
It's a sign that the deep ocean plumbing has fundamentally changed.
I remember when this cold blob was first being widely discussed, there was a pretty robust counter-argument, right? That this might just be an atmospheric effect, something to do with industrial aerosols.
Oh, that debate was intense for years. A lot of climate models that included aerosol effects suggested the AMOC might temporarily strengthen or at least stabilize because the cooling from pollution was balancing the warming from greenhouse gases.
But that's been resolved now.
It has. Recent critical research published in 2025 provided the resolution. This study showed that only the climate models that feature a significant weakening AMOC can correctly reproduce the location, the depth, and the persistence of this cold blob pattern over the historical record.
So the models that didn't have a weakening AMOC just got it wrong.
The models that relied only on aerosol changes, or that predicted an AMOC strengthening, were found to be inaccurate for this specific region.
So the cold blob is the AMOC's smoking gun. It's the visual confirmation that the engine is, in fact, slowing down.
It is. The fingerprint of the cold blob points overwhelmingly toward a long-term forced circulation slowdown, driven by freshwater, not just atmospheric noise. And this recent finding reinforces the validity of the proxy data that first raised the alarm years ago.
Let's talk about that historical context, because that gives us a sense of just how unprecedented this current weakening is.
Right. We have substantial evidence from paleoclimatic proxy reconstructions. These reconstructions rely on analyzing sea surface temperature patterns, particularly the ones that show that characteristic signature of a cold northern Atlantic and a warm southern Atlantic.
The pattern you'd expect with a weak AMOC.
Exactly. And these proxies suggest a significant long-term decline. Current estimates are that the AMOC has slowed by about 15% overall, compared to pre-industrial conditions. And disturbingly, it's now calculated to be at its weakest state in at least 1,500 years.
That 1,500-year number is powerful. It means that even the variability that happened during, say, the Little Ice Age or the medieval warm period wasn't enough to push the AMOC this low.
That is the implication. This isn't just natural variability. This appears to be a forced, sustained decline. Statistical analysis has refined the timeline even further, pointing to a weakening trend that's been continuing since the late 1930s.
And the direct measurements support this.
Critically, yes. This is all supported by the direct observational data from the Rapid Array, which detected a significant downturn starting around 2010-2011. The data points, from proxies to models to direct measurements, all align on the fact that the system is weaker now than it has been in many centuries.
The accumulation of all these early warning signs brings us directly to the heart of the current scientific tension. I mean, there's consensus that the AMOC is weaker, but there's a huge... and, most importantly, how close we are to the tipping point.
That's right. And we can frame this as the decline camp versus the stability camp. Because as your listeners' sources show, this isn't just an academic disagreement. It has massive implications for policy timelines.
Okay, so let's start with the decline camp. What's their case?
Well, in the decline camp, you have studies relying heavily on those SST proxies, the cold blob signature, and the high-resolution direct rapid observations from after 2010. Their data indicates an ongoing, even accelerating, weakening.
And this camp is the one looking for signs of critical slowing down.
They are, and this is the camp that produced the most alarming forecasts.
And this is where we have to introduce the work of the Danish sibling scientists, Peter and Suzanne Ditlevsen. Their 2023 study was a major focus for our listener, and it shook the world because it gave us a specific date range.
It really did. The Ditlevson's work used a specific type of early warning signal detection. They looked for increasing variance and autocorrelation in sea surface temperature data, stretching all the way back to 1870.
Data that correlates with AMOC strength.
Very strongly. But unlike traditional climate models, which project physical processes, they treated the AMOC as a complex empirical system. They tried to statistically predict when it would tip based on how its observed behavior was changing.
And what did the empirical statistical analysis predict? It was a bombshell.
It was. Based on their findings, they projected a potential collapse starting anytime between 2025 and 2095. Their median, or peak likelihood, was specifically calculated to occur around the middle of this century. Some follow-up analyses even cited the year 2057.
That is an extraordinarily narrow and alarming window. It suggests the tipping point isn't some distant theoretical threat, but something that could happen within the lifetimes of most people listening right now.
It's a policy nightmare. And, of course, it was immediately met with a lot of skepticism, mainly from the stability camp, who argue the Ditlevsons were relying on potentially flawed data.
Right. That's the crux of the methodological dispute.
It is. The stability camp includes recent high-profile studies, like one from 2025, that analyzed reconstructed trends from air-sea heat fluxes from 1963 to 2017. Their argument is that sea surface temperature measurements, the proxies the Ditlevsons and others used, are highly unreliable over long periods.
Why unreliable?
Because SST is sensitive to so many other variables. Short-term atmospheric changes, shifts in wind patterns, they can all affect the surface temperature.
So they're saying the signal of AMOC weakening in the SST data is just noise.
Essentially, yes. The stability camp argues that a more robust measure is the calculated air-sea heat flux and the density distribution from subsurface observations. And they claim that data does not show a significant sustained decline over the past 60 years.
So their conclusion is that the AMOC is fine?
Not that it's fine, but that it's more stable than the collapse studies suggest. They contend that while short-term variability is high, the overall trend doesn't point to an imminent collapse. They concluded that a strong decline over the last 6 decades seems very unlikely. This allows them to push the high-risk scenarios much further into the future.
It sounds like a fundamental disagreement about which data set most reliably measures the engine's internal health. So where does the official global consensus land in this fight?
The official position from the IPCC's 6th assessment report in 2021 remains cautious. It held that there was medium confidence that an abrupt collapse would not occur before 2100.
Which is a classic consensus position.
It is. It balances the conservative models with the more alarming empirical forecasts. But the high-risk forecasts, particularly that mid-century projection from the Ditlevsons, directly challenge this more conservative view.
It seems like the debate has forced the modeling community to try and be more precise about the actual physical tipping threshold, moving away from just timelines and towards specific, actionable metrics.
That's probably the most productive response to the conflict. Model refinements have started to quantify the tipping risk by tying AOC dynamics directly to the surface buoyancy flux. That's the net input of freshwater versus the density loss from warming.
And these new studies project a critical temperature threshold.
Yes, a threshold that, if we cross it, commits the AMOC to collapse.
And what is that number?
The current best estimate from the complex models is a critical temperature threshold of plus 3 degrees Celsius of global warming relative to pre-industrial levels.
Plus 3 degrees.
Right. And the research provides a range of certainty, spanning between plus 2.2 and plus 3.9 degrees as the trigger level. Once the forcing reaches that level, the freshwater input from melting ice is virtually guaranteed to overwhelm the system's ability to maintain its saltiness and density.
How soon do we hit that 3-degree threshold under current emission trajectories?
Under the high-emission scenarios, like RCP 8.5, that threshold is projected to be reached just after 2050.
Which confirms the risk is substantial this century. It aligns pretty well with the Ditlevson timeframe, just using a different method.
It does. But here's the crucial caveat. The risk is not limited to the worst-case scenario. Even in the middle-of-the-road scenario, RCP 4.5, a collapse is still statistically possible. It depends on the model's sensitivity and the initial state of the ocean.
So the takeaway is what?
The takeaway is this. The AMC is undeniably on course to tip if sustained emissions continue to push global temperatures higher. The disagreement is really only over the exact decade we cross that invisible finish line.
Let's turn now to the consequences, because the urgency of this whole debate really stems from the sheer magnitude of the disaster. As we said, once the AMOC is gone, it's not a temporary climate blip.
That cannot be overstated. A complete AOC shutdown is largely irreversible on human timescales. Model simulations suggest recovery could take thousands of years.
We're talking about committing the planet to a new, profoundly different climate state for millennia.
We are. And the historical record gives us the maximum credible disaster scenario. You can look at past AMOC collapses, like the Dansgaard-Ogier events.
What happened then?
During the last glacial period, the AMOC switched on and off repeatedly, triggered by huge releases of fresh water from melting ice sheets. These events were associated with temperature changes of up to 10 degrees Celsius in the North Atlantic region.
10 degrees.
10 degrees. And critically, these monumental shifts didn't take centuries to unfold. They happened over just decades. This historical precedent proves the system is capable of rapid, massive climate reorganization.
So let's drill down on the regional impact in Europe. The core consequence is profound, widespread cooling. But this is happening while the rest of the planet is still warming due to CO2.
It creates this regional paradox. The primary effect for Western Europe and the North Atlantic is the loss of that 4 to 10 degrees Celsius heat benefit we talked about. Regional temperatures are projected to fall dramatically.
So that cooling effect would dominate the local background warming.
It would, resulting in a sudden, sharp reversal of temperature trends for that region.
We're talking about winters that are structurally different from anything modern Europe has adapted to.
That's absolutely correct. The modeled scenarios are chilling. One study looked 200 years into the future, under a scenario where the AMOC collapsed against a backdrop of 2 degrees of global warming.
And what did it find?
It showed infrastructure shattering cold. London, for example, could face cold extremes approaching minus 20 degrees Celsius in 1 out of every 10 winters.
Minus 20 in London. That's unimaginable for its current infrastructure.
And Scandinavia faces far worse. The projections show Oslo plummeting to around minus 48 degrees Celsius during these extreme cold events.
Oh my God.
This is a level of deep freeze that requires specialized winter planning, heating capacity, and infrastructure resilience that just doesn't exist outside of, the most northern Canadian or Siberian cities.
And this extreme cold is amplified by another critical feedback mechanism: sea ice.
Yes. The extensive cooling allows sea ice to rapidly expand, reaching the coasts of northwest Europe in winter. And sea ice is highly reflective. It increases the albedo of the region.
So it reflects sunlight back into space.
It reflects solar radiation that would otherwise warm the water, which further amplifies the cooling, locking in the new cold state. This shift would fundamentally alter Europe's societal priorities, turning climate adaptation away from heat stress and toward unprecedented chronic cold.
If the AMOC is the planet's circulatory system, its failure must trigger cascading effects far beyond the North Atlantic. What happens to the global water cycle?
The disruption is global. The AMOC is linked to the location of the Intertropical Convergence Zone, the IPCC, which is this massive band of low pressure that dictates where tropical rainfall occurs.
And an AMOC shutdown would move it.
It would cause the IPCC to shift southwards. This means severe disruption of precipitation patterns. We would see catastrophic drought in regions that rely on the Afro-Asian monsoon, threatening the food security of billions.
And at the same time,
we'd see increased storm frequency along the North Atlantic tract itself, even as it cools.
And what about sea level rise? That's a key concern for coastal cities.
A collapse is expected to accelerate sea level rise along the U.S. East Coast, particularly along the mid-Atlantic bight.
Why there specifically?
It's because the AMOC provides a slight gravitational pull, essentially tilting the sea surface by pulling water north. When the current weakens, that pull disappears, and the excess water piles up along the U.S. coastline.
How much are we talking?
It could potentially add a foot or more of sea level rise on top of the thermal expansion we're already committed to.
That's a compound effect that coastal planners need to be thinking about right now. And what's the unexpected link to southern Africa?
Well, the ocean is a closed system. The sudden heat loss in the north has to be balanced elsewhere. The shutdown causes a relative warming of the southern hemisphere and its atmosphere.
And this warming is particularly pronounced around southern Africa.
Exactly. It threatens regional biodiversity. An AMOC collapse reduces the transfer of warm Agulhas current waters from the Indian Ocean into the Atlantic. This massive system shift threatens the delicate balance of regional ecosystems that rely on that current stability.
Finally, we have to consider the economic toll, the sheer cost of this systemic failure, even if it's just weakening and not a full collapse.
The economic implications are staggering, and they're often underestimated in standard climate damage models. A weakening AMO directly reduces the ocean's ability to take up atmospheric CO2.
So the planet loses one of its major carbon sinks.
It does, which means the rate of warming accelerates. The CO2 lingers longer in the atmosphere, driving up the temperature faster.
And that has a cost.
It exponentially increases what's called the social cost of carbon, the SCC. That's the estimated dollar damage from adding 1 extra ton of CO2 to the atmosphere.
And factoring in an AMOC collapse would send that number skyrocketing.
Factoring in a collapse, combined with the cascading effects like monsoon failure destroying agriculture, would increase the SCC to the point where the net cost to society and economic damage would reach trillions of dollars globally. It's a permanent negative structural shock to the global economy.
Given the irreversible nature and the, frankly, existential stakes of an AMOC collapse, the discussion inevitably turns to radical, often controversial interventions, what the sources call alternative climate intervention. If we can't stop the melting fast enough, can we manually adjust the ocean? The Bering Strait Dam, or BSD, is a geoengineering concept focused specifically on manipulating the AMOC mechanism itself.
It's an idea with a really interesting history. It actually dates back to Soviet scientists in the late 1950s who wanted to warm Siberia.
But it's been revived for a different reason.
Modern research has revived the dam concept specifically as an emergency measure for AMOC stabilization. It would essentially act as a counter-dilution measure. The concept is to stop the freshwater from reaching that critical sinking zone.
But the Bering Strait is thousands of miles away from Greenland. How does that narrow channel affect the entire Atlantic?
It's all about the flow.
Mhm.
Currently, there is a natural northward flow called the Bering Strait Through Flow, or BST. This flow transports almost 1 Sverdrup of North Pacific surface water into the Arctic Ocean.
And 1 Sverdrup is a lot.
1 Sverdrup is 1 million cubic meters of water per second. It's roughly 18 Amazon rivers flowing at once.
Wow. Okay, that puts it in perspective.
And that Pacific water is less salty than the Atlantic water. The BST carries about 80 millisverdrups of net fresh water into the North Atlantic via the Arctic. It's a constant source of dilution.
So the intervention goal is simple. Close the strait with a dam, block the fresh Pacific flow, and allow the North Atlantic to get salty again.
That's the theory. Closing the Bering Strait would prevent this fresh water from weakening the AMOC. Model simulations confirm the immediate impact. Under present-day conditions, an artificial closure is projected to significantly strengthen the AMOC by about 2.5 Sverdrups.
So it's a massive artificial boost of salinity.
It is. And it works not just by blocking Pacific freshwater, but also by restricting water exchange between the Arctic and North Atlantic, which collectively reduces the overall freshwater influx to those critical sinking zones.
So it can work, at least in the models. What did the simulations say about the timing? Is this something we have to build immediately?
The results were surprising. They showed a surprisingly large window of opportunity. The models indicated that a closure can be an effective strategy to prevent a CO2-induced collapse, but only if the AMOC is still relatively strong.
If the North Atlantic is still salty enough.
Right. And in certain high-emission scenarios, the closure could be delayed up to 150 to 250 years after the CO2 forcing begins and still be preventive.
That's a huge window. It suggests the dam is a last resort option that doesn't need immediate implementation.
It does. It gives us time for CO2 mitigation to hopefully work.
And this is a massive catch. This is the part that turns this from a silver bullet into a double-edged sword. The intervention itself becomes a critical risk factor if it's timed incorrectly.
This is maybe the most profound finding of the geoengineering research. The timing is absolutely non-negotiable. The research shows that if the AMOC is already severely weakened, if its strength has dropped below a specific critical threshold, somewhere between roughly 7.8 and 9.8, Sverdrup's implementing the closure is counterproductive.
Counterproductive how?
Instead of saving the AMOC, it actually speeds up the collapse.
That's completely counterintuitive. Why would stopping the freshwater inflow when the system is weakest and needs salt the most hasten its death?
It's a complex feedback loop related to Arctic dynamics. When the AMOC is strong, the open Bering Strait freshens the water, weakening the circulation. Simple enough.
Right.
But when the AMOC is critically weak, the system stabilizes around a different set of dynamics. At that weak state, the open strait has a paradoxical stabilizing effect.
How can it be stabilizing?
For a very weak AMOC, the open strait allows some dense, salty water to leave the North Atlantic. And, critically, it reduces the import of low-density sea ice into the sinking zones. It keeps the North Atlantic slightly warmer and less stratified in the deep winter.
So implementing the dam too late essentially disrupts a fragile, stabilized, collapsed state, kicking it back toward extreme instability just when it can least afford it.
Exactly. It results in a counterproductive tipping. This means the decision to build this massive piece of infrastructure is completely dependent on knowing the AMOC's exact internal state. Not just that it's declining, but exactly how much strength it has left.
And if we get that measurement wrong,
We actively accelerate the catastrophe we're trying to prevent.
that level of risk forces us to confront the ethical and societal consequences of betting the entire planet on a single, massive technological fix.
The scientific community uniformly stresses that CO2 mitigation remains the preferable and necessary option. The BSD is a desperate temporary fix at best.
And it introduces a significant moral hazard.
It does. The argument is that the perceived existence of a clean, easy technological fix, like a dam, might reduce public and political will to pursue the essential, difficult emission reduction policies. It gives climate skeptics an argument to delay action.
And even if we build it successfully, the fundamental threat is still there because the underlying CO2 is still accumulating.
Which leads directly to the risk of termination shock. Geoengineering only treats the symptom, the AMOC state. It does not remove the cause.
The CO2 and the stored heat.
Right. If the BSD intervention were suddenly stopped due to technical failure, economic collapse, geopolitical conflict, whatever, the stored warming and the underlying freshwater forcing would rapidly reassert themselves.
And the rebound would be catastrophic.
It would be immediate and severe, leading to a climate shock far more swift, potentially more damaging than if the collapse had simply occurred naturally years earlier. It's a climate time bomb.
So we've taken a deep dive into the lifeblood of the Atlantic, the AMOC. We've analyzed the critical debate over how close we are to its collapse. From the alarming mid-century prediction put forward by scientists like the Ditlevsons, to the high stability estimates favored by those who rely on air-sea heat flux data.
We detailed the chilling, dual global consequences. That profound regional cooling that would plunge Europe into hyper-cold winters, coinciding with catastrophic monsoon failures and accelerated sea level rise globally.
And finally, we analyzed this radical, double-edged solution, the Bering Strait Dam, a project that has to be executed with surgical precision or it risks hastening the very catastrophe it was designed to prevent.
And that requirement for precision is the final, profound sticking point. The analysis confirmed that if the AMOC weakens too much, dropping below that roughly 7.8 sphere rip threshold, closing the Bering Strait would actually make things worse.
Which raises an extraordinary policy challenge for you, the listener. How do you make a timely decision on whether to greenlight a massive, irreversible geoengineering project when the data needed to confirm the system's current critical strength is fundamentally lagging?
Because the direct measurements from arrays like RAPID are essential. But recovering that equipment, processing the data, it all takes time. You are always operating with a data lag of 18 to 36 months, sometimes even longer.
So you're always looking in the rearview mirror.
Always. If the tipping point is predicted for, say, 2057, policymakers in 2055 might be basing their decision to deploy the dam on data from 2052, while the system may have already crossed that irreversible threshold in the intervening years.
It's a race against a clock we can't read in real time, and it forces us to ask, is the only ethical window for such an extreme intervention one that requires us to preemptively deploy the solution based solely on model projections years before we can empirically confirm the danger? That is the terrifying decision facing humanity this century.